This video is about easy real-time architecture, the right way to develop software to control complex machine, medical device, or assembly line. That is why it's easy. It takes only a few months for one developer to develop and test a fairly complex system. Here is the overall big picture of the easy real-time architecture. When the main scheduler runs, it can create many more schedulers running simultaneously. Each scheduler here is checking for event, then is dwelling at the delay. After that is execute the operation. When working on an operation, the scheduler might spawn off another task or thread. This way, the system will be more responsive to events and arrive data. With events, delay, and action parameter, scientists can control the machine down to the very fine detail. Let me step into the scheduler to load up an operational demo script. Normally, we run a script of complex automation workflow on the machine to produce oligo, execute PCR operation, or processing an IC for semiconductor industry, etc. E parameter stands for event parameter. So let's say that we have an event checks for true. We check to see if tag 2 is done. Tag 2 is another scheduler running thermocycler 1 script. And when that script is done, tag 2 will be set to done. Then this event check for true become true. When event become true, the scheduler will go on to dwelling state. If there's a delay is like a settling time, then the scheduler will execute the action. This action here command all running script to pause. A parameter is the parameter of action or operation. In this case, we can put pause, stop, or resume. Because each step can be executed asynchronously, we need to show the status here. You can set the timeout. You can also set the error message, what to show up inside the error log message. Here are the 9 principles shaping the development of this easy real-time architecture. Low latency is one of the first principles we are already making sure that our easy real-time must meet. Then scalability. Here you can run many scripts simultaneously. Here's 1, 2, many more scheduler in auto and manual mode. Normally, most of the system out there, you just need one scheduler, but here we give you as many as you need. We divide the system into sub-modules according to modularity principle. We break them up for easy controlling and maintenance. Here is an example system. We have a gantry which is moved in X, Y, Z direction. Is moving between the plate. You can think as there are 96 pipettes on the gantry head transferring fluid between the plates. This plate laying in this nest here. KX2 is another module with robotic arms of wrist, elbow, gripper, it picking up place, then move the place around in this nest. This arm is transferring plate from biodot to the machine nest. The biodot is a droplet dispenser, dispense fluid into the plate. After dispensing the fluid into the plate, KX2 carry the plate into the machine nest. Gantry work on the plates by dip its head pin into the plate to transfer fluid to another well on the same plate or to a different plate. After that, KX2 arm pick up the process plates and put it in the thermocyclers or chiller. As you can see, we break the machine into modules. Here we have thermocycler 1, we have thermocycler 2, a 96 pipetter, or you can call it 96 pinhead, on the XY gantry here to be select which head to be dipped into the well of the plate. This pinhead or pipetter here, that's how fluid is transferring between the plate. It's a complex machine, so we have to break into module like this for easy control, develop, and maintenance. Easy to understand is the goal of this architecture, so you can design and code at the same time. This cutting down the time because the code is simple and straightforward that scientist, developer, project manager, engineer, and quality control validator can look at the sequence of operation while they are in the meeting. Everybody can look at the same code instead of having to go through the flowchart, class diagram, a sequence diagram, or any UML documentation. Then transfer that knowledge onto the code. Software developer can explain and develop right there. So we can all look inside the code because the code is short, simple, and straightforward. That's written in C#. So here, this is the code of the state machine. You're looking at 16 state of pick and place sequence of operation. We have a task, like I already mentioned earlier. Here, all these tasks. One of that tasks is the pick and place task. We have 16 state for this operation. When we have a design or an issue, the software developer can pull up the code and everybody can look at it. It's tell you move plate here and get motor get current position. Then people can ask, why you do that? Why you do this? Everybody can explain and can understand at this level. If for some reason the main developer got hit by the truck, because it's easy, a new developer can come in and understand. Or if he need to be trained up, it can be done in a few hours to understand the code and he can begin to work. We only need one experienced developer per system or per machine. So the project planning and implementation will have faster decision making, result in consistency of coding and design implementation by using this easy real-time architecture. The scheduler is only about 2,000 lines of code. Each module here is around 2,000 lines. Here, let me see how many line is about little bit more than 2,000 line of code per module. So that is not much. With one developer, this can cut the cost down a lot. The code will be more reliable because the development is quick. I would say within a few days, one module can be developed and ready to hardware hookup testing. Testing and debug need to be intensive to produce high quality software. Because of this real-time architecture, the development and design will be quick. Most of the time, we'll focus on fixing issue report by QC tester, like the hardware failure and error recovery. This raises the reliability of the software up high. For security, we have different level of password to protect against unauthorized access and data breach. For maintainability, because of the easiness, it make it easy to maintain the system over time. So let me run the demo so you can see what is really going on. So first line is pick and place, and the second line now it's launch a new scheduler. There are a total of 4 new scheduler. Here is thermocycler 2 and thermocycler 1. Let me put them aside. So we have IO pinhead, which is the pinhead, so that we can look at the pinhead and see how they are running. See, all this pin is selected. Pinhead here is like a little pipette. One of the scheduler running this chiller script. Here it set the temperature differently after a certain sequence of operation and synchronously waiting for that temperature to reach. We can set the delay here for how long to chill. Done. The main scheduler is timing out here. Is wait for the event. Here the event parameter, the scheduler is checking for true. This event check to see if tag 2 is done, which means checking for thermocycler 1 script running to be done. Checking for so long is not done within 10 seconds. The scheduler is timing out. This is only for demo, but in real life you want to set this timeout to be longer, a little bit longer than what you expected from the thermocycler 1 script running scheduler. So that is the summary of the easy real-time architecture. If you have any question or you are interested in this architecture and need consultant work, please contact us at longhonglei@yahoo.com or leave a comment. I will get back to you. Thank you for watching.